Okay, lessons in 6 and 7 are on accumulation functions, which how we have also been covering in previous parts of our year together. So we'll just do maybe two problems here. We'll do examples 1 and 3, and that should prepare us for both lessons 6 and 7. Okay, so we'll let g of x be this antiderivative from 0 to x of f of t dt, where f is a function whose graph is shown. These are called accumulation functions because we're going to be adding up the area inside of the particular problem. So first we'll complete a table of values. So x, g of x, well, if we were to calculate what happens at 0, we would be calculating the integral g of 0 would be the integral from 0 to 0. And I'll stop there because if we integrate from 0 to 0, that means we're going to get no area whatsoever. So the answer to this problem right here is going to be 0. Okay, next, g of 2. So g of 2 is going to be an integral from 0 to 2 of our function. So if I go up to our picture, I can see from 0 to 2 means I am looking from here to here, and I need to find the area under the curve because that's what that's what an integral is referring to. So how I like to do these is I like to kind of subdivide them into their separate areas. So I'm going to first cut down there at 1, and notice that I have 1, 2, 3, 4 blocks. So I'll call this 4. And then from here to here I have 1, 2, and then I have this triangle that has a height of 2 and a base of 1. So its area is 1. And so I'll call this 3 in order to represent what its entire area is. So the integral from 0 to 2, the area under the curve from 0 to 2, is simply going to be 7. So let me label that in with 7. Okay, moving on to f or g of 4. G of 4 is the integral from 0 to 4. We've already done the area from 0 to 2, so I just have a little bit more to add on, which comes from here and here. So what is the area of that triangle? Well, 2 times 2 is 4. Half of 4 is 2, so that area is 2. And so the integral from 0 to 4 is going to be the 4 plus the 3 plus the 2, which makes a total of 9. 4, 7, 9. So there is our area then. Okay, now the fun parts. What is happening with g of 6? G of 6 all of a sudden means now we have to go into the negative area because 6 brings us down below the x-axis. So this looks to be a 2 by 1. 2 times 1 is 2. Half of 2 is 1. So the area of this region down here, be careful, is negative 1 because it's below the axis. And therefore, when we want to know what the g of 6 is, which is the area from 0 to 6, or the integral from 0 to 6, we got all the way up to 9, but then from 4 to 6, we're doing a negative 1. We're losing one value, and therefore, the output's going to be 8. On that last little part then, as we get out to 8, means now we're actually subtracting all of this, which is 1, 2, 3, 4 by 2. 4 times 2 is 8. 8 divided by 2 is 4. So this additional part must be a minus 3. And so if I minus 3 more from our current accumulation, we'll now have 5. And so that's how you fill in the table of values doing separate integrals. What is g prime of x and what is g double prime of x? Well, g prime of x is the derivative of this antiderivative. And so the answer there is simply just going to be f of x by the FTC. How about for g double prime? G double prime of x means that we will have to find the derivative of the derivative, and the g prime, or the f, is the picture that's given here. So notice that we would be calculating slopes in this case. So the g prime is going to be different answers based on what intervals you are on. See, the slope up here is 0. The slope from here to here looks to be a 2 over 1 in a negative direction. The slope from here to here is a negative 1. And then the slope over this interval is 2 by 4, so that's a 1/2 in a negative direction. So that's all of the different g double primes on the different intervals. And this first interval was for 0 less than x less than 1, and then the negative 2 was for 1 less than x less than 2, and then it was from 2 to 4, and then finally on that last one it was from 4 to 8. 4 to 8. So we get a whole bunch of different g double primes, which are the derivatives of the picture, which is the derivative of the accumulation function. Okay, then find the largest open interval for which g is increasing and the largest interval where g is decreasing. So g is the function up here. G prime tells us whether it is increasing or decreasing, and as mentioned here, g prime is simply f of x. So this question is equivalent to asking where is f, which is the derivative of g, positive or negative? This would be f positive, and this would be f negative. And so the biggest intervals for those are, well, where is the biggest interval where f is positive? That's from 0 to 4. 0 to 4. And for 2, that's the biggest interval where f happens to be decreasing, where g is decreasing, which means f would be negative, and that is from 4 to 8. So again, to analyze increasing, decreasing of g, we have to take its derivative, which means we analyze f. Are there any local extrema? Well, let's do a first derivative test on this one, since we have one place where g prime equals 0, that occurs at 4. And before that point, we can see that g prime is positive, and afterwards it is negative. So there is a local minimum. I can see that there is a local minimum. So we would say local min at 4, at x equals 4, which gives me increasing and then decreasing, which means this is a max. Positive derivative increasing, negative derivative decreasing. So we have a maximum that occurs at 4 with value, and remember we did those up here, so the value is 9. Okay, we don't have a local min, but we're going to have an extremum, right, an absolute minimum, either on the left or the right endpoint. We don't know which until we look up at the fact that we already found the values at 0 and at 8 at the two endpoints. So we can see, of course, that 0 is less than 5, and so we would say that there is an absolute min at x equals 0, which has a value of 0. So that completes the extrema of g of x. Okay, how about for concave up and concave down now? So now we would be analyzing the second derivative, which was located up here. So for the second derivative, if that's our second derivative, we could say that g is concave up where we have a positive second derivative. Notice the second derivative is never positive, so we would say this never happens. And where is g concave down? G is concave down where we have a negative second derivative. So that's on all of these intervals, except for the 0 interval where it's not concave down. That's constant. So here we would say g is concave down on the intervals from negative, or from 1 to 2, union 2 to 4, union 4 to 8. 4 to 8. Okay, next part is to find the average value of f of x over the given interval. So the average value would be adding up f of x between 0 and 8 with respect to x, and then dividing by the length of the interval, which is 8. Finding the area from 0 to 8 is equivalent in our problem, if you look back, to just simply finding out what is g of 8. Right? G of 8. Because g was defined to be the integral from 0 to whatever, and we just want to find the integral from 0 to 8. G of 8 was already calculated, right? G of 8 is already 5. So that means that this answer is going to simply become 1/8 of 5, which of course is 5/8. So you see how that original piece of information really feeds us everything we need. And then the last part of the problem is to sketch the graph. So I'm going to refer back to my table that I got from up here, and I'm going to insert that into my graph, going through 0, 0, 2, 7, 4, 9, and then 6, 8, and then finally 8, 5. 8, 5. Keep in mind that we're always concave down, and you can see that we're now increasing or decreasing on these particular intervals. So that means over here we must be increasing concave down, increasing concave down, decreasing concave down, and decreasing concave down. So it appears that our graph looks something like this, and that's consistent with the information above, right? We're getting our absolute minimum occurring at x equals 0 with a value of 0, and we're also getting this local max that's occurring at 4 with a value of 9, always frowny, we're always concave down, and that brings all of the information together. Okay, that's long enough because it's got a lot of pieces in there, so why don't we leave the rest of them for us to do in class and as homework.